Okay, so how does life on Earth get from just one species to the, unbelievable variety we see all around us today? It's a huge question, right? Well, that's what we're tackling today, the grand sweeping story of evolution. Let's get right into it.
And to get our heads around this, let's start with a classic puzzle. I mean, this is a puzzle that really helped change how we see the world. It goes like this. How does just one type of bird, landing on some remote islands, eventually become 13 completely different species?
Well, believe it or not, this is exactly what happened with the famous Galapagos finches. I mean, just look at the incredible variety of beak shapes here. Each one is like a perfectly specialized tool for a different kind of food. And the crazy part, all of them, every single one, came from a single ancestor species that somehow made its way to those islands millions of years ago. So how on earth does that happen?
All right, to really get the answer, we need to pull back. We have to zoom way out and look at the big picture of evolution, the super long-term history of life itself. And this big picture story has a name, macroevolution. Now, we're not talking about the small, year-to-year tweaks within a population. Nope, this is evolution on an epic scale, the blockbuster movie version that plays out over millions of years, with its story written right there in the fossil record. So this is a great way to see the two scales of evolution side by side. On the left, you've got macroevolution. Think of it as the whole epic novel. And on the right, you have microevolution. That's like the individual words and sentences. It's the small generation-to-generation shifts in the genetic makeup of a population. But here's the key takeaway. You can't have the novel without the words. Macroevolution is just what happens when all those tiny microevolutionary changes add up, over and over and over again for a really long time.
Okay, so if these small micro changes are the building blocks, what's actually driving them? What's the engine behind all of this? Well, it's a concept you've probably heard of, natural selection.
And the process, as Darwin figured out, is it's so elegant and logical. It's basically a four-step dance. Step 1, overproduction. Most organisms have way more offspring than can possibly survive. Step 2, genetic variation. All those offspring are a little bit different from each other, right? Step 3, competition. Because there are too many of them, they have to compete for resources to stay alive. And that leads to Step 4, differential reproduction. The individuals that just happen to have the best traits for that environment, they're the ones who are more likely to survive, have their own offspring, and pass on those winning traits.
So we've got our engine, right? Natural selection. Now imagine you let that engine run for thousands or millions of generations. And then you throw in a little twist, like splitting a population in two. When that happens, something pretty amazing can happen. A whole new species can be born.
This process has a name too. It's called speciation. And the absolute key ingredient here is something called reproductive isolation. All that means is that two groups that used to be part of the same species get to a point where they just can't interbreed anymore and have viable offspring. They've gone their separate ways. So, what causes a split like that?
Well, sometimes it's pretty straightforward. It's a physical barrier. A new mountain range pops up or a canyon forms, and suddenly a population gets split in two, just like with these spotted owls. Once they're separated, each group starts evolving on its own, adapting to its unique little corner of the world.
But it doesn't have to be a giant mountain. Sometimes the barrier is behavioral. Check out these two meadowlarks. Physically, they could interbreed, but they don't. Why? Because they use completely different songs to attract a mate. It's like they're speaking different languages. No song match, no mating.
And then sometimes it really is just all about timing. Take these two skunk species. One is ready to mate in the late winter, the other in the fall. Their biological calendars just don't line up at all. They're living in the same place, but they might as well be on different planets when it comes to breeding. That's called temporal isolation.
Okay, so let's zoom back out again. We've seen how one species can split into two. Now imagine that process of speciation happening over and over and over across millions of years. When you look at the whole tree of life, you start to see these incredible, large-scale patterns emerge.
Now, scientists have spotted a bunch of these major patterns, but we're going to focus on three of the really big, dramatic ones today: mass extinction, coevolution, and adaptive radiation.
First up, mass extinction. And yeah, these are catastrophic events, absolutely devastating, but they can also be a powerful creative force. Think of it like a giant reset button. When tons of species disappear, it suddenly opens up the playing field, creating all these new opportunities and empty jobs, basically, for the species that survive to move into and diversify.
Next, we have coevolution. This one is fascinating.
It's like an evolutionary arms race, or maybe a dance, between two species. They get locked into this relationship where they're constantly influencing each other's evolution. A classic example is a flower's shape evolving to perfectly match the beak of the hummingbird that pollinates it, and vice versa. Each one drives the other's changes.
But the pattern that brings us full circle, the one that really gets back to our finch puzzle and explains how one species can become 13, well, that one might be the most spectacular of all.
It's called adaptive radiation, and it's basically an evolutionary explosion. You have one single ancestral species that gives rise to a whole bunch of new species pretty quickly. It radiates out into all these new forms, and each new one is specially adapted for a different job or a different environment.
Then that's it. That's the solution to our puzzle. One type of finch lands on the Galapagos Islands, and what does it find? A whole bunch of open jobs, these unoccupied niches. So, through speciation and natural selection, its descendants just radiated out, developing those perfect beaks for every possible food source. Seeds, cacti, insects, you name it. And that is how one species became 13. So the big takeaway here is that evolution isn't always this super slow, gradual crawl. Nope. When new opportunities suddenly open up, like a brand new chain of volcanic islands, speciation can actually happen pretty darn fast to fill all those empty roles.
And that leaves us with a pretty powerful final thought. If adaptive radiation is kicked off by new habitats, well, think about our world today. It's changing faster than ever, isn't it? From climate shifts to cities expanding. So the question is, what new and maybe challenging worlds are opening up for life right now? What new adaptive radiations could be happening right under our noses? It really makes you realize that the incredible story of evolution is still being written. Thanks so much for joining me.